Greetings from Pluralsight. In this movie, I want to talk about how Microsoft implements deferred execution in LINQ. This tutorial assumes that you know how to write a class that implements the IEnumerable interface and the IEnumerator interface. The 50 or so standard query operators of LINQ are implemented as extension methods on the IEnumerable of T interface. These extensions can be found in the enumerable static class, which is contained in the system.link namespace and resides in the system.core.dll assembly. Of these, those operators that return a single scalar value, such as the count operator, or the average operator, or the sum operator, etc., need to traverse through all the elements in the sequence in order to return their result. Such operators are termed as greedy operators. And the phenomena of having an operator to traverse through all the elements of an enumerable in order to fulfill a request is termed as immediate execution. However, sparing these few greedy operators, most of the other operators in LINQ offer what is known as deferred execution. That is, they defer or postpone the execution of the state machine to the client code. These operators are likewise termed the lazy operators. This means when you call a lazy operator, it does not traverse through the elements of the enumerable to give you its result. It defers the traversal to the client. Let's see what I mean by looking at some code. Let us assume that we need to implement the filter operator represented by the where extension method. If we were to write our own implementation of where, our intuition would probably lead us to this. I've put this in a separate static class named greedy extensions in the namespace greedy operators. We receive an enumerable and a predicate, and all we do here is traverse through the enumerable, evaluate each element in the enumerable against the predicate. If it matches, add it to the list that is to be returned. The problem with this implementation is that it goes through all the elements in the sequence in order to process its result. This is a greedy implementation, and this is not how Microsoft implements where or many of the other lazy operators in LINQ. In fact, let's run this code to prove our point. I have a student class and a school class. A school is an enumerable of student. I have a custom implementation of the IEnumerator of T interface implemented by the student enumerator class. If I run this code using the Microsoft implementation of system.link.enumerable.where and put a breakpoint just before we execute the for each loop in the client's main method, you will see two things. First, the runtime type returned by Microsoft's where operator is some strangely named class that we are not aware of, but it is surely not a list of T, as we did return from our implementation. The second thing you'll notice is that the debugger did not break into the getEnumerator or the moveNext implementations we wrote in evaluating this query. Now let me comment out the Microsoft implementation and instead reference our implementation by adding a using statement to our greedy operators namespace. This time if I run the code, you will see that the debugger breaks into both the getEnumerator for the school class and the moveNext on the student enumerator class, because we've already executed the state machine or triggered a traversal through the sequence in our for each loop in the greedy where operator implementation we wrote. This implementation is bad because it incurs a performance penalty. What if the enumerable being traversed was being streamed, or for all practical purposes was an infinitely large enumerable with data coming from a remote web server? In these scenarios, calling our where operator would mean the client code having to wait while we traversed through the sequence ourselves. This would not only degrade application performance and user experience, but it would just not be acceptable in a business scenario. And it wouldn't make a very good case for LINQ. It is for this reason that where possible, LINQ defers the execution of the enumerator state machine to the client. You might think that's just not possible. How would, for example, a where operator filter out the elements without actually going through each element in the sequence? And here's the trick. The lazy operator is able to defer execution by simply repackaging all the information it receives into a custom enumerator that applies the operation to be performed in its moveNext method and simply returns that enumerable. This is how a greedy operator works. On the right side you see the server enumerable, in the middle is your operator or extension, and on the left is the client code. The greedy implementation simply traverses through each element in the enumerable. If the element is not a match against the filter or operator, it is discarded. Any match that is found is added to a new enumerable, and that enumerable is returned to the client. The client has to once again iterate through the newly received enumerable. As against this, a lazy implementation simply takes the source enumerable supplied and the predicate supplied as an argument and creates a new enumerable that packages both of these. Further, it implements a custom enumerator which, if and when executed, would at that time filter the elements of the sequence. It packages all of this in a new enumerable and returns this new enumerable as it is to the client. Let's put this to code. This time we'll write a lazy implementation for where, just like Microsoft wrote. I'm going to put this lazy implementation in another static class named lazy extensions and put that in a namespace called lazy operators. All I have to do here is return an object of a class that we're going to write, which implements IEnumerable of t and receives all of this information, that is the source enumerable and the predicate. You can call this class anything, it really doesn't matter what you call it because the user isn't interested in the type information for this class. I'm calling it the where enumerator of t. Let's go ahead and create this class and write a constructor that receives these arguments and stores them into private fields. And our class implements the IEnumerable of t interface, so let's write the implementation for that. Now, from the getEnumerator method, I need to return an object of another class that implements IEnumerator of t for this enumerable. I could do that in a separate class, or I could make this class itself implement both the interfaces. I'll make this class itself implement IEnumerator of t as well. Remember, it's not important which class implements either of the interfaces. You could do it either ways. The only two important members to look at are moveNext and the current property. In fact, all of the magic is going to be in the moveNext method. Let me back up a little bit. You know that when a for each loop executes an enumerator, the first thing it does is it checks whether the sequence has a method named getEnumerator. In this case, we would give the client object an object of the whereEnumerator class. And when the client attempts to iterate over this enumerable using a for each, the first method to be called would be the getEnumerator. And since our getEnumerator returns a reference to the same object, the for each would call the moveNext on our whereEnumerator class to find out if it could move to the next item. Now, in our moveNext, since we do not know the exact runtime type of the IEnumerable, it could be a list of t, it could be an array, or a custom type like our school class that implements the IEnumerable interface. Therefore, all we're going to do is rely on the underlying enumerator to tell us how to move next. Now, if I took a local variable here called source enumerator and assigned it the source enumerable.getEnumerator here, it would return a new instance of the underlying enumerator every time moveNext was called. And that would not only waste memory, but it would be incorrect because it would instantiate a new state machine every time. So, I'm going to cache a reference to the underlying enumerator once at the class level and initialize it in the constructor. Also, I'm going to keep a reference to the current item at the class level. And then in our moveNext, all I do is I keep asking the underlying enumerator if it can move next, and while it can, I evaluate the current item returned by the underlying enumerator against my predicate. If it matches, I return true, so that moveNext may be called again. I keep doing this until the underlying enumerator runs out of items, that is, its moveNext returns false. And that's basically it. If I run the client code now, first I'm going to have to change the using statement in the client code to use our lazy operator. And if I run this code, you will notice again, unlike in the case of greedy operators, but very much like in the case of the Microsoft implementation, the debugger did not break into our getEnumerator or moveNext methods even until after the query was constructed. You will also notice that the runtime type of the query variable is our deferred execution.whereEnumerator. And if I reflect on the contents of the query in the debugger, it shows us that the results view is still in the state where the results of the query have not yet been evaluated. This is true deferred execution. I hope you enjoyed this video and learned something new with it. My name is Satyaish Chakravarti, and you've been watching a presentation from Pluralsight.